Hi, everyone. Can you hear me? Hello? Thank you. Appreciate that. I put some links to notes in the header, and I'll throw it in the chat as well. I filled them out when I went through this by myself, and I posted what I'm calling the answers also, and those links should work forever. I hope everyone's doing great today. We're going to be talking about kinetics. I'm Meg Hennessy. I'm the head of chemistry content at RV. Jessica couldn't be with us today, so I'm taking over. All right. I was just going to jump into it. A lot of times at the top of the slide, what I'm going to show you is the assessment statements from the chemistry subject guide. So I'll have the applications or the understandings you're supposed to have just to keep us a little bit on track. I assume that you're pretty far along in knowing kinetics, so I think I'm going a little bit fast. But if you have any questions, please feel free to drop them in the chat. I just posted the link and I will do it again, but it's on a few of the slides coming up as well. That's the filled one. And I think that's the unfilled one. I just typed it, so make sure I don't have a silly typo. There you go. So the rate of a reaction is the change in concentration with respect to time. And we can talk about an instantaneous rate or an average rate. And the difference is if we're going to take a tangent to that curve. So an instantaneous rate would look like taking just a little tangent to the curve. That would be the instantaneous rate at this point. Or an average rate would be saying what's the average over the first 40 seconds. We would look at 0.0, we would look at 0.40, and we would take something like a secant, the rate of this line. Ooh, it's hard to draw a straight line sometimes. But you can see that I didn't actually choose a product, I chose a reactant. And you can see that those rates are negative. We always report the rate as a positive number. If you were to consider my reaction where nitrogen dioxide is turning into nitrogen oxide, you might notice that the coefficients of these two things are the same, and the rates of these two things are the negative of each other. And that's kind of cool. So the rate of the reaction is some number, but we are gaining product at exactly the rate that we're losing reactant. O2 has a different coefficient, and because O2 has a different coefficient, you're going to see that it has a rate that's about half as big. So if you knew how fast one thing was being formed or being used up in a chemical reaction, you could use the coefficients in the reaction to determine how fast another thing was being formed. So NO is being formed at twice the rate of O2. I show on my left axis, on my y-axis, the concentration of those different things. Concentration is actually a little bit hard to measure in the lab. In the lab, you normally see um, other things being measured, like mass or absorbance or pH or conductivity or volume or pressure. So those would be reasonable things to actually measure on the left-hand side, but those are all going to be essentially proportional to the concentration. So that's what we mean. Can anyone else see the links that I'm posting? Oh, no, you can't because I hit the wrong button. Hello, are you guys still here? Oh, thank goodness. I'm so sorry. Zoom crashed as soon as I hit the chat. Like it just went away. Oh my goodness. Okay, so let me try again with sending those links. Everyone say something really kind to themselves or the world so that it doesn't mess up again. I'm just going to show them to you. Okay. And I'll show them again in just a second, but just in case you wanted to go there, that should get you there. All right. I was going to say one more thing about clock reactions before everything went to heck. And clock reactions, you might have done like the thiosulfate clock reaction or the iodine clock reaction. That's when you watch a reaction occur and you stop your timer when the solution turns black or when you can't see the cross anymore. And there you measure time for the reaction to be done. And if you're interested in the rate of that reaction, you can't like take a tangent curve or anything. You're just going to say that the rate is proportional to 1 over the time it took for the solution to turn black or for the cross to disappear. That was a question on one of the May exams. And so I thought it was interesting because we are absolutely taught in class that the units of rate are moles per decimeter cubed second. I was really nervous answering that question because the units of rate calculated for the clock reaction were just per second. So I thought it was kind of a crazy thing. So I wanted to make sure I said something about it today with you. Okay, so just a general idea of where we are with rates, just to make sure we're all awake. I came up with some easy starter. How would we find the initial rate of this reaction and how would we find the average rate over the first 4 minutes? So initial rates are going to come up again a little bit later. Initial rate means the rate at time equals 0. And to do that, we're going to draw a tangent to this curve at time equals 0. And we're going to find the slope of that line to the best of our ability. I did it on the next page, so I didn't have to dazzle you with my graphing skills quite yet. If we wanted to find the average rate over the first 4 minutes, we would take the point at 0, we would take the point at 4, we would connect them with a nice secant line, and we would take the slope of this line. Something I do notice is that the rate of this reaction is getting slower over time, and I think that's going to be important for us to understand rates a little bit better. So here you go, if you want to see that drawn better. And here are the links again. I was hoping people might come in a little bit late, but with my killing Zoom, maybe that's not an issue anymore. You can see I just calculated the rate of that tangent line at t equals 0. I got 0.69. The number isn't very important. But then when I calculated the average rate of the first 4 minutes, you can see I got a much smaller number. I got 0.23. So we're finding that the rate does slow down as the reaction occurs, and I'd like to understand more about that. I'm going to give you a second to read this problem. Think about how you might answer this. I'm going to see if there's any questions in the chat. Oh my goodness. Thanks for letting me know. I was told that the link isn't active for you, so I'm going to go make sure that I have the permissions set properly. I, of course, checked that I could open it, which seemed like a good place to start. How many of you are examining in November? Or now, if you like those words? Couple. I hope you feel like your studying's going great. I'm glad you're here today. I fixed the link, I believe. It'll take it a second to update, but they should be there. Again, thank you for letting me know. Thank you so much. All right, so graphing is important, and certainly on the paper 1Bs, we're seeing more and more questions about graphing and about interpreting graphs. If we wanted to know how the concentration of a reactant changed with time, we would expect that the reactant's going to be used up. So we would draw usually a nice exponential decay curve. That's like our default shape. It obviously shouldn't cross the x-axis. The concentration should not be a negative number. And if we wanted to deduce the rate at a certain time, like this time t, we would draw a tangent line to it and point out that the slope of this line, the gradient of this line, is the rate of the reaction. And in a textbook, that's considered a 4-mark problem. And I would be very happy to find that on my exam. Collision theory is a big idea early in the kinetics unit. It says that for a reaction to occur, what has to happen is that the reactants have to collide, they have to run into each other, and they have to have enough energy to overcome any barrier, and they have to have the proper orientation. And so I have this example of hydrogen and iodine coming together, and you can see the iodine molecule on the left, and you can see the hydrogen molecule on the right. And if they try to intersect or combine tail to tail, that's not going to work. They're not going to make the right product. But if they come together face to face, like they do in the bottom one, that collision could be successful. That's the orientation effect, or the proper geometry. So for a reaction to occur, the two reactants, or however many reactants, have to collide with the correct geometry, or in the right way. When they do collide in this right way, you can see what must be happening is that the HH bond must be breaking, the II bond must be breaking, and the HI and HI bonds must be forming. But since I haven't really formed those bonds and I'm putting in the energy to break the other bonds, that's a really high energy thing. We refer to this as a transition state. And the transition state is the local maximum on the energy profile. The energy profile shows how the energy changes as the reaction proceeds. So on the y-axis, I'm plotting energy. On the x-axis, I'm plotting reaction coordinate. Reaction coordinate is a strange way of saying that on the left side, I have all reactants, and on the right side, I have all products. There are a few things that you can take away from this, but one of them is up here. The transition state is the highest energy place on this. You could also see that my reaction is slightly endothermic. That is, the products have more energy than the reactants. You can also see that I've labeled the activation energy, which is the minimum energy that a collision must have in order to be successful. And I underlined minimum because when, it hasn't been for a few years, but when this question has been asked on exams, the word minimum has been required. Activation energy is the smallest amount of energy that the reactants have to have in order to collide successfully. Now there's a relationship between having enough energy and the temperature. So the temperature, measured in absolute units or Kelvin units, is proportional to the kinetic energy of the particles. So if you wanted to make sure that particles had more energy, you could just increase the temperature of the system. All right, that's collision theory in one slide, I hope. More common than trying to define collision theory is to say, how do these different things affect the rate of the reaction? So I tried to identify 4 different ways that we could affect the rate of the reaction. We could increase the amount of stuff. If it's a gas phase, that means we would increase the pressure. If it's a solution phase, that means we would increase the concentration. When we do that, there are going to be more collisions because there are going to be more things to run into. If you put more people into the room next to you, it would be easier for you to collide with them because they'd be right there. You wouldn't have to be moving any faster. We could take a solid and we could grind it up. We're not going to change its concentration, but we are going to give you more surface with which to react. We could increase the temperature of the reactants. That's going to do 2 things. The first thing it's going to do is if you go back to that room with the people, if there's more temperature in the room, the people are going to be moving faster. So they're going to collide more frequently. And one more time, I've underlined the word frequently because this is the thing that was most missed on the May exams. They say, they being the students who are writing the exam scripts, will answer a question that says, if you increase the temperature, there are more collisions. And I can't award the mark for more collisions. It has to be more frequent collisions or more collisions per unit time because the molecules are moving faster. Also, when you increase the temperature, more of the collisions will have enough energy to overcome the activation energy. So temperature helps us in 2 ways. It will increase the fraction of successful collisions, and it will increase the frequency of collisions. Finally, we can add a catalyst, and what a catalyst does is it provides an alternate pathway with a lower activation energy. If you lower the activation energy, then more molecules, when they collide, will be able to overcome it because it's easier. So just in terms of collision theory, I put together 2 multiple choice and 1 little short answer. I'm going to give you a minute to read through those and make sure that this makes some sense. And again, feel free to throw things in the chat as you think of them. Yep, we guys have notes for this study session. I think the way to be the least disruptive about this. When the computer crashed, I lost all my saved things, so I'm just trying to get it back. Okay, there you go. No worries. Thank you so much for asking. I didn't realize you hadn't seen it for a minute. All right, so I tried to give you a minute to work through these. In terms of collision theory, how does a decrease in pressure affect the reaction rate? 2-mark question. The first mark is going to be it slows down the reaction or decreases the reaction rate. And the second mark is going to be the frequency of collisions is lower. And it's probably because the molecules are farther apart. What do catalysts do? What catalysts do is they provide an alternate pathway that lowers the activation energy, which means that more of the molecules will have enough energy to successfully react. So they increase the fraction of successful collisions. So I think that's choice B. So I was asked about the amount of gas particles on each side, or is that only something for equilibrium? So if we increase the pressure, sorry, we decrease the pressure. I'm not going to change that. If we decrease the pressure here, You guys have studied Le Chatelier's principle in R2.3, and that's going to remind you that we have 2 moles of gas on the left and we have 3 moles of gas on the right. And so the reaction would shift to the left. Decrease. Oh, no, it's going to shift to the right. It's going to shift to undo the change. How do we match that to what we're seeing with the rate? When you decrease the pressure, the rate is supposed to go down. Well, let's imagine that we're going to decrease the pressure of just the forward reaction. I have 2 particles that have to collide. And so it's going to happen less often because there are less of those particles. But if I think about the reverse reaction and I decrease the pressure, I now have 3 particles that have to do something. The likeliness of those 3 particles colliding at a lower pressure is going to be even lower. So I'm going to slow down the reaction even more for the reverse reaction. So when I was at equilibrium, the rate forward and the rate reverse were equal to each other. If I decrease the pressure, I'm not going to be at equilibrium anymore because I'm going to preferentially slow down the reverse reaction. As I re-achieve equilibrium, that is, as those 2 rates become more like each other again, what I'm going to need to do is I'm going to need to build up more of those products so the rates can again be equal to each other. So we do see the same effect when we apply Le Chatelier's principle to an equilibrium reaction. But when a question asks specifically about collision theory, they're really talking about just the forward reaction or the reaction that they've written. The last question that I have here is about iodine and hydrogen reacting together. It looks like an endothermic reaction. And why do we sometimes not get the product? Remember, for a reaction to be successful, it has to have the right orientation and it has to have enough energy to overcome the activation barrier. And so it must be true here that these 2 molecules don't have enough energy. I can try my Le Chatelier's thing briefly again. Let me make this. Let me insert a piece of paper. There must be some way to do that. Okay. I have 2 moles of gas on the left-hand side going to 3 moles of gas on the right-hand side. And the question that I got in the chat, and if anyone wants to ask, feel free to add something there, was what happens to this system at equilibrium? So I'm going to change that arrow to be an equilibrium arrow. And the first answer I'm going to give you is that if the pressure decreases, Le Chatelier tells me that the reaction will shift forward to make more gas, to undo the stress. You took away particles, and so the reaction is going to shift forward to make more gas particles. In collision theory, what we learn is that when you decrease the pressure, you slow down a reaction. For a reaction of only 2 molecules, you're going to slow it down a little. For a reaction of 3 molecules, you're going to slow it down much more. It's going to be even harder for 3 things to find each other if the system is more dilute. So that means we're not at equilibrium anymore. The 2 reactions do not have equal rates. Remember, the definition of equilibrium is that the forward reaction and the reverse reactions have equal rates. So the forward reaction right now is going faster than the backward reaction because it was slowed down less. What that's going to do is it's going to make more products. As we make more products, I deleted that, isn't that funny? As we make more products, what's going to happen is the rate of that reverse reaction is going to slowly speed up until it matches the rate of the forward reaction. So just like Le Chatelier taught us, the reaction is going to shift forward. We're going to make more product. It's going to be to make those 2 rates equal to each other. All right, moving on. A couple more questions to practice about collision theory. At SL, this is probably one of the 2 big ideas in the unit. The first one says, we're going to state a reason for why this is going to affect the rate. So if we increase the concentration at constant pressure, how is the rate going to be affected? I know there's lots of words everywhere, but this is a question just about if we change the concentration, what happens to the rate? And the answer is going to be as the concentration increases, the rate increases. And to get our mark, we're going to say there are more frequent collisions. Not more collisions, but we're going to include that word. If we increase the temperature, what's going to happen to the rate? It's going to increase, we're told. Why? This is always a 3-mark question. Temperature is proportional to kinetic energy, or the average kinetic energy. So when we increase the temperature, the molecules move faster or have more kinetic energy. Because they move faster, they collide more frequently. But also, because they have more energy, the fraction of successful reactions will be higher. Because more molecules have an energy greater than the activation energy. And just to reinforce the 2 major precepts of collision theory, number 1, molecules have to overcome, they have to collide with the right orientation. And they have to have enough energy to overcome the activation barrier. So that to me is collision theory. I hope it feels good to you. Let me know if you have any questions. Otherwise, I have this curve that shows the formation of hydrogen gas, the volume of hydrogen gas in kind of crazy units, 100 cubic centimeters as a function of time. And I'm asked to look at this graph and to change it. Instead of using magnesium ribbon, I'm going to try to use magnesium powder. If I change from magnesium ribbon to magnesium powder, I'm increasing the surface area. When I increase the surface area, I'm going to increase the frequency of collisions because there is more magnesium to collide with. But I'm not changing the amounts of anything. And so I need to draw a graph that shows a faster rate, but forms the same amount of hydrogen. So it needs to plateau at the same value, but it needs to be steeper or have a higher rate. If I decrease the amount of magnesium and I decrease the concentration of the acid, then I expect that I'm going to have a reaction that is both slower and makes less product. When we do this reaction, we almost never do this particular one by mass. We always do it by volume. I liked this question when I taught it in class. I thought it was interesting, so I threw it in here. The problem with trying to measure this one by mass is that this solution weighs at least 50 grams and it's in a beaker. And so we're talking about having 150 grams worth of stuff and it's going to lose hydrogen. Hydrogen is extremely light. We have like the molar mass of magnesium is like 24 grams per mole. And we have 0.3 grams. So we have like 100th of a mole. So we're going to make like 100th of a mole of hydrogen. and a hundredth of a mole of hydrogen is going to have a weight of like 0 or a mass of like 0.02 grams. You could never actually see that be evolved on the types of balances I have in my lab. So we always measure volume because it's a much more precise measurement than mass, given the tools that we have access to. If you want to measure the mass change of a reaction that evolves gas, we usually do something like calcium carbonate, making carbon dioxide. And that's because carbon dioxide has a much, much bigger molar mass. I got another question about the Le Chatelier's principle thing. I'm happy to talk about that at the end, but I'm going to move on for a little bit. So I promise I'll get back to it. So we already drew a little energy profile earlier, but just to make sure you know how to do all of this, we need to be able to draw it with a catalyst, without a catalyst, for endothermic and for exothermic, and to label everything. And so we discussed how the x-axis should be the reaction coordinate, the y-axis should be energy, and we showed that the reactants appear on the left and the products appear on the right. If I had an exothermic reaction, the products would be lower in energy. Where did that energy go? It was given off to the surroundings. If I add a catalyst, what I do is I provide an alternate pathway with a lower activation energy. This is the original activation energy. With a catalyst, I would lower it. Exo means exothermic. I'm not sure where I wrote that, but exo means going out into the surroundings. So exothermic means that you release heat to the surroundings. So that means if you have an exothermic reaction occurring in a cup of water, the reaction, the water will feel hot. So if you put a few pellets of sodium hydroxide into a beaker of water, the beaker will feel hot because the reaction sodium hydroxide solid becoming sodium hydroxide aqueous is exothermic. So where does the heat goes? It goes to the water that you're actually putting the sodium hydroxide in. When you burn a fuel, that's exothermic. So when you have a candle next to you, you can feel the heat coming out. The heat is going to the surroundings. The transition state is the local maximum. I think we did it. Too many. The other picture that we draw a lot in this unit is the Maxwell-Boltzmann curve. The Maxwell-Boltzmann distribution is just like one of the distributions you may have learned about in your math class. So if you have a binomial distribution or a Gaussian distribution, it tells you the frequency on the y-axis. And it tells you like what you're measuring. In this case, it's energy on the x-axis. And the shape of the Maxwell-Boltzmann curve is such that it starts at the origin. It never crosses the x-axis. And it has a peak that's a little bit asymmetric. So the peak is just a little bit on the left-hand side of the average. So I overestimated that here probably. We know that temperature is proportional to the average kinetic energy of a system. So I was interested in how this curve might change if I changed the temperature of the system. So if I were to change the temperature of the system, I know that I would have to increase the average kinetic energy. And to increase the average kinetic energy, I would have to move that line, to the right, because this is my energy axis. And so to do that, I have to start at the origin. I have to asymptote toward the origin. And so what I'll get is a curve that looks flatter and has a maximum that's further out to the right. Now, some of you are going to say, uh-oh, She goofed and she made the average the most probable. That's because we don't really care a whole lot in chemistry about that distinction. I just wanted to say that the curve is asymmetric on purpose, but when I'm sketching this on an exam, I'm okay with not worrying, like with not being able to tell that difference. What I do need to be able to believe when I draw this curve is that the area here under the black curve is about the same as the area here under the red curve. That is the total area. So that's why it has to come down or get flatter. Because if I want the peak to move to the right, the pancake is going to be squashed down. I'm not totally sure I understand the last question I got in the chat. So I'm going to guess that the question was, what does it look like if we decrease the temperature? If we decrease the temperature, then it's going to look more like this. It's going to be tall and over to the left-hand side. Again, I would like to believe that the area under the curves is about the same. You can see that I didn't do as great a job there. It's just a feeling. No one's gonna measure this. So this is the highest peak. Because again, the area needs to be the same under each of these curves. So at low temperature, we're going to have a very tall, skinny peak. And at high temperature, we're going to have a short, fat peak. If we were to integrate the area under this peak, it would represent the total number of particles in the system. If we're not changing that, then it needs to be the same for all the pictures. If I wanted to show you how many molecules could successfully collide, then I would need to include one more thing on my graph, and that would be the activation energy. Conveniently, I have an axis that is energy. And so what I do is I just cartoon in some value that represents the activation energy. And if I wanted to show you how many molecules had more energy than the activation energy, I would shade in all of the molecules represented by the curve to the right of my activation barrier. So those are the ones that have enough energy to react at the very low temperature. Whereas at the high temperature, you can see many more molecules have enough energy to react. Similarly, if we were to add a catalyst, we would say that catalysts provide an alternate reaction pathway with a lower activation energy. So we could just draw a second activation energy with a lower value and see all of these new molecules are now able to react. So why does lowering the activation energy or adding a catalyst increase the rate of the reaction? It does so because more molecules now can have successful collisions. A higher fraction of the collisions will be successful. So I think this looks a bit of a mess. I think I have some cleaned up pictures on the next page. When the temperature increases, that's the picture on the left, you can see that the curve gets lower and flatter. But you can also see that this whole area, the lighter gray area, represents molecules that can now react that couldn't before. When we add a catalyst, you can see that we don't change the curve. We're not changing the temperature of the molecules. What we are doing is lowering the standard for a successful collision. And so again, in the light gray, you see all of the new reactants that have enough energy now, and suddenly all of the collisions that will be more successful. All right, that's Maxwell-Boltzmann. Here's a quick little multiple choice. Which one of these graphs shows the effect of adding tungsten on a chemical reaction? So you can see that the before without catalyst is the dotted line. It's the same in all four pictures. how would I show you the effect of adding a catalyst? And hopefully many of you said C. A couple of you put it in the chat, which I appreciate. Shows me I'm not alone. You can see that we've lowered the activation energy. And so again, all of these new molecules are going to be able to react and make us some ammonia. This is what happens if we lower the temperature. This is what happens if we raise the temperature. And it's unclear how we would do this. This would be like removing a catalyst in D, so I'm not going to write a note there. To me, that's SL kinetics or SL 2.2. I'm now moving into an HL idea, which is that a reaction could actually occur in a couple steps. And when a reaction occurs in a couple steps, that energy profile that we were just drawing just becomes a little bit more complicated. Instead of having one maximum, you could have two or three maximums because they're going to be not one step, but two or three little steps. And so I chose something that has two steps, and I can see it has two steps because there are two maxima. Right here, this local minimum is called the intermediate. It's a stopping point along the way. Now, you might also notice that we have two different activation energies. And based on that, maybe we could infer which step is fast and which step is slow. Yes, I mean, I'm going to have questions at the end for SL, but if you do not want to listen to any of this, SL students are free to go. So as you're looking at those two activation energies, I hope you notice that this activation energy is very big. And so few molecules in the system would have enough energy to overcome it. So this is going to be the slow step. So I've gotten a few questions in the chat that say, what's going on? I've done the SL content to the best of my ability. I am now moving into some of the HL content. At the end, I will answer any questions y'all may have. So I appreciate those of you who are checking out. It was great to have you. And those of you who want to stay on, cool. The second step must be the fast step because it has a much lower activation energy. So I thought that was interesting. This overall reaction shows the reactants at a higher energy than the products. And so this overall reaction is exothermic. There's a new vocabulary term here other than intermediate that I already forgot. We call this slow step the rate determining step. So in IB chemistry, we get to make the approximation that says that the rate of a reaction is determined by the rate of the slowest step. So some of you might have to commute to school. You also do a lot of other things to get prepared to school, but at least where I live, just the time it takes to drive is by far the longest thing. And so we're going to pretend in IB chemistry that the rate of me getting to school only depends on how long it takes me to drive there. It doesn't depend on how long it takes me to brush my teeth or to put my shoes on. Those are just inconsequential. If you go on in biology, chemistry, physics, you're going to see that there are other approximations that we can make that are really cool. But we're just going to make like the first one is like the slow step is the one that matters. I was asked how I knew that this reaction was exothermic. So delta H is going to be the enthalpy of the products minus the enthalpy of the reactants. And so here you can see the products have less energy or enthalpy than the reactants. And so this value is going to be negative. And so it's exothermic. To determine the slow and the fast, I just looked at the activation energies of the two steps. This activation energy for the first one is big, and this activation energy for the second one is small. And so I said that the reaction step with the really big activation energy is going to be the slow step. I'm good. So this idea of elementary steps or mechanisms comes up a lot in the organic unit, where we actually draw out with curly arrows the mechanistic steps. So if you're thinking about an SN2 reaction, you're going to show your nucleophile coming up to your whatever. I don't know why I do it quite so square, but you know, we're going to show it coming up to this primary halogenoalkane. And we're going to show that the chlorine's going to leave. And we say this happens in a concerted step to make that intermediate. Right? So we're showing you like blow by blow what happens in this reaction. And if instead of drawing this as SN2, I decided to draw it as SN1, I would draw different things. I would say, well, first thing that happens is the carbon-chlorine bond breaks. And the next thing that happens is the nucleophile attacks the carbocation. So we see these elementary reactions as being really important when we talk about organic chemistry. But they're really important everywhere. They allow us to learn a lot about how reactions take place. And just like in organic chemistry, we need to have some sort of a model for how they happen. And so for this reaction with ozone in the atmosphere, someone has proposed two steps. Now, these two steps rely first on a chlorine atom attacking ozone, pardon me. And then later, what happens is that this product, the chlorine monoxide that was made, is used up when it reacts with monatomic oxygen to regenerate the chlorine and some oxygen gas. So this is a two-step reaction, but overall what's happening, let's add those together. So if I add them together, I'm going to have chlorine and ozone and oxygen and chlorine monoxide on the left. And on the right, I'm going to have chlorine monoxide and O2 and monatomic oxygen. Oh my God, no, I'm not. Monatomic chlorine. And another oxygen. I think I added those right. So I added up all of the things on the left and all of the things on the right. And I noticed, just like in math class, there's some things that cancel out. The first thing that I noticed that cancels out is the ClO. And the second thing I noticed that cancels out is the Cl. And so this overall reaction is that ozone and oxygen come together to make two O2s. So at the top, we proposed a reaction mechanism, but at the bottom, we're seeing the reaction that's actually happening. That's what we're trying to understand. How do we make diatomic oxygen in the atmosphere? Two of the things that canceled out, the ClO and the Cl, play different roles in this reaction. The Cl is a catalyst. It is used in the first step and regenerated. To be used again. So one chlorine monoatom could react with this ozone and then be reformed at the end of this reaction to react with another one and another one, like we see in the radical chain reactions in R3.3, the propagation steps. On the other hand, an intermediate in this is going to be ClO. That's something that's made. Spelling is so hard. In one step, and then used up later. So in an SN1 reaction, the intermediate would be the carbocation intermediate. That's what we call it. We talk about how it could be more stable if it's a secondary or a tertiary carbocation intermediate. An intermediate is something that we're proposing, but we don't necessarily have direct evidence of. And so we would have to go into the lab and try to find more evidence that it indeed did exist. Too many. So because understanding reaction rate is a little bit difficult, we don't always have the ability to come up with this reaction mechanism. What we say is that you need to do experiments to determine what the rate law is. And so for any chemical reaction, I claim that you can write down a really generic reaction rate law. And that says that the rate of the reaction is equal to the rate constant times the concentrations of the reactants raised to some power, which is known as the order. But I really carefully changed the letters. The coefficient for reactant A in my chemical equation is not the power that I'm raising A to in the rate law. They're not the same. They are only the same when they are elementary steps. So the problem has to say that you're looking at a mechanism, you're looking at an elementary step. The rate law must be determined experimentally. The rate constant includes everything that we learned about when we were talking about collision theory. We said that we needed to have enough temperature in Kelvin for the particles to have the kinetic energy to overcome the activation barrier, and that the particles needed to collide with the correct orientation. So K takes into account those things. If we make the temperature higher, the rate constant will increase. If we make the activation energy lower, the rate constant will increase. If we stir, if we grind a solid, we would increase some of the orientation pieces. We would make it more likely that two molecules could collide with the right orientation because we're making them strike in different ways. And so we would increase the rate constant. The other thing the rate depended on was the concentration. I've just pulled that out to show you that the rate is going to be two things, the rate constant K, and then the concentrations of the reactants raised to some powers. My expression for the rate constant is known as the Arrhenius equation, and that equation is in the data booklet. It's in the first thing with all of the different formulas. So no worries. It's written both in the form with the e to the minus EA over RT and in that linear form. And we'll come back and use those in a little bit. I want to focus first just on the rate law and how it is we could try to deduce the orders N and M. And there are three ways we can do it, because when I look at this crazy reaction that shows over here 14 reactants, there's no way that all of those things are coming and colliding with the right orientation at the right point in space. It's inconceivable. I can barely get 3 students to do the right thing at the right time. There's no way 14 reactants are going to come together perfectly. And so the 3 ways that we usually deduce the rate law are using the method of initial rates, which is mathematical, by comparing data to some common graph shapes, which is graphical, and then by a guess and check, where we guess a mechanism and compare it to experiment. The method of initial rates is always presented as a table. And what it looks like is you do a bunch of experiments, and in each experiment, you change the concentration of the reactants and you measure the rate right at the beginning. So that tangent line right at t=0. And you try to figure out what's what. So I know that the rate can be written as the rate constant times the concentration of the reactants raised to some power but I know those powers are going to be the same for all of these experiments. And so I could compare some experiments. So I could write down this expression for experiment number 1. I would say that the rate of experiment number 1 has to be equal to the rate constant that I don't know, times the concentration of but1ene raised to the nth power times the concentration of HBr raised to the nth power. And I could do the same thing for experiment 2. I could say 3.0 times 10 to the minus 3 is equal to K times the concentration of but1ene times the concentration of HBr, both raised to those powers, just like before. And what I notice is that this simplifies a whole lot. First, I notice that this is just 2. And that K over K, well, that's 1. And 0.2 to the n over 0.1 to the n, I could write as 0.2 over 0.1 to the n, I guess, if I wanted. And these two things cancel because they're the same. And so I can figure out here that n is in fact 1. So I figured out the order with respect to but1ene by doing this kind of complicated ratio using my definition of the rate law. So I call that the slow way. But what I noticed with the slow way is what it relies on is the fact that the concentration of one thing was constant, while the concentration of the thing I was interested in changed. So I compared how the thing I was interested in that case it was but1ene, changed with the rate. So if I look at experiments 2 and 3, I can see that the concentration of but1ene is constant. The concentration of HBr doubles. And the rate doubles. And so it must be true that this reaction is first order in HBr as well. The rate changes exactly the same way the concentration changes. And so the overall rate law here must be but1ene to the first power and HBr to the first power. Now rate has units of moles per decimeter cubed second, moles per decimeter cubed second. And it's equal to K times the concentration of but1ene times the concentration of HBr, a reaction that is second order overall. So if I wanted to solve for the units of K, I would just have to take all of those units and put them over on the left-hand side, and I would get the units of K to be decimeters cubed per mole second, which is kind of gross, but something I probably need to practice doing because I know it's a pretty common question that they want the units. What's more traditional when we do this, and probably I should have done it first, is to say what's the value of K. But I think we're all better with our calculators maybe than we are with our units. We know the rate for, say, the first reaction was 1.5 times 10 to the minus 3 moles per decimeter cubed second. And that has to be equal to K times the concentration of but1ene times the concentration of HBr, both raised to the first power, which is 1. And so we could write down that K is equal to 1.5 times 10 to the minus 1 decimeters cubed per mole second. And the rate is equal to K times the concentration of but1ene times the concentration of HBr. Hopefully we did that right. So there are a few ways to deduce the units of K. The way I showed you right here was just plugging in the units for everything in the equation and then solving it algebraically. I have a few more examples. So let's see if this makes some sense. What I mean by examples is there are some common orders. And so one approach is if you find that mathematics or manipulation of the algebra not fun, you can memorize what the units of K would be for different orders of reaction. So the idea is that in every case, on the left-hand side, we have rate, and on the right-hand side, we have K times the concentration raised to some power, which we call the order. The units of rate are always the same. They're always moles per decimeter cubed second. And the units of A, concentration of A, are always the same. They're moles per decimeter cubed, but we're going to raise that to some power, and that power is going to change. So for a 0th order reaction, N is 0, and rate and K have the same units. For a 1st order reaction, I have moles per decimeter cubed second on the left is equal to K times moles per decimeter cubed. So the units of K must be per second. And so that's what I wrote down at the bottom. So that is an approach to try to figure out the units of K, is to be confident that you can write down some of the more common ones, or to think about how to rearrange the algebra up here. So we practice the method of initial rates really fast. Another way that people could ask you about rate laws or determining the order with respect to something is comparing it to what we commonly see. And what we commonly see are 0th, 1st, and 2nd order reactions. A 0th order reaction is one where the rate is constant. So you can see that in my bottom graph. It's showing you the rate doesn't change as the reaction takes place. As the concentration of A changes, the rate is constant. And my example of this is reading. So like for my birthday, I might get a couple of books. I enjoy reading at night, but the pace that I read at doesn't change even if there are more books available. It's independent of the concentration of books. I just read like a page per minute. So if there's another book on my nightstand, that's cool. I can't wait to read it, but it's not going to make me read the books I have faster. The rate is constant. I'm just casually reading at night to fall asleep. So it's just going to be a straight line. So my graph down here is showing you that the rate is constant. And my graph up here is showing you the number of pages that remain per unit time. Every day I read so many pages. So it's going down linearly. That is what a 0th order reaction looks like. A 1st order reaction is significantly more common. All radioactive decay is 1st order. Here, the rate is proportional to the concentration. You can see that here. The rate is directly proportional to the concentration, and the slope of this line, or the gradient of this line, is the rate constant. This says when you have a lot of something, the reaction is going to be fast. And when you have less of something, the reaction is going to be slow. So you can think about your chemistry class. If everyone in your chemistry class flipped a coin and then looked at which side was up, so heads or tails, I would expect that if I had all of the students who saw a head on their coin sit down, half of the students would sit down. So if there are 30 people in my class, 15 people would sit down. If we did a second round, 8 people would sit down. There are fewer people playing, and the rate of them sitting down is slower. So the rate is proportional to the number of molecules, exponential decay. A 2nd order reaction shows that the rate is proportional to the concentration squared. So you can see that parabola here. And so this means that the reaction is really sensitive to how much stuff is there because every A has to go find another A. So when there's a really high concentration, it's really easy for them to bump into each other. And so the rate is super high here. But as time passes and as you use up your reactant and an A still has to go find another A, they're going to be really far apart, really difficult to find. And so the reaction slows way down. And so while the difference in shape between first and second order is sometimes hard for me to see, I'm going to try to put one on top of the other for you to show you that a second order reaction is like faster initially and slower later on. These curves come up a lot in the multiple choice part. So here's a little method of initial rates for you to practice. I have a tertiary haloalkane reacting with water, undergoing nucleophilic substitution. So I feel like I can write down the answer. I just want to see if the numbers support it. So what is the order of the reaction with respect to each reactant? And so our shortcut for doing that was holding one thing constant and looking at the change in the other thing. Here the change is the concentration of water doubles. And when the concentration of water doubles, what happens to the rate? The rate is not changed. So because the rate is not changed, I'm going to say that it is 0th order. The rate is independent of the concentration of water. Try number 2. I'm going to hold the concentration of water constant. I'm going to see how the concentration of the halogenoalkane is changing. It's changing by a factor of 2, or it's doubling. And the rate over here is doubling. So they're behaving the same way. The rate is directly proportional to the concentration. It's first order. In the tert-butyl bromide, whatever I'm going to call that. If we wanted to write down the rate equation, we write rate on the left, the word rate or the letter R is equal to the rate constant K times the concentration of the reactants raised to their orders. Anything raised to the 0th power is 1. So you could write this, or you could write that. If we wanted to calculate the value of the rate constant, we would just plug in any one of these reactions. So we could say 4.0 times 10 to the minus 6th moles per decimeter cube minute is equal to K times the concentration of the halogenoalkane. That looks like 1.0 times 10 to the minus 1 moles per decimeter cubed. And so K is going to be equal to 4.0 times 10 to the minus 5. And it's going to have units of minutes to the minus 1. Ah. All right. I hope that felt okay. Now we're given some elementary steps for a reaction. And we are asked to try to figure out if these steps would support what has been experimentally found to be the rate law. So it says experimentally, the rate law is second order with respect to NO and first order with respect to O2. And it says we've proposed an idea. We believe that this reaction takes place as two steps. Both of them are bimolecular. That means both steps involve the collision of two molecules. There are two reactants on the left-hand side. And the first one is fast and the second one is slow or rate determining. So because the second one is the rate determining step, I would write down that the rate of that elementary rate determining step is just the rate constant times the concentrations raised to their coefficients. This is the only time I'm allowed to use the coefficients in the equation. And it's because I'm saying that that reaction is like really the collision of a nitrogen trioxide and a nitrogen monoxide, that they're coming together. What is the probability that those two things are going to come together? Well, the probability is going to be proportional to the concentration, because the concentration is telling you how many of those molecules are around in some amount of space. So a concentration is a lot like a probability of finding a molecule somewhere. And so if I multiply two of those together, that's going to be the probability of two things being at the same point in space. So with that, some of you are going to notice that I have included something I'm not allowed to include. That is to say, I've included an intermediate. NO3 is made in step 1, but then consumed in step 2. And intermediates, because we can't prove they're there, we can usually look at a reaction and know what we started with, and we can often measure what we made, but it's difficult to see what's made along the way. And this is just a proposal. We're not sure that this is right, so we can't have a rate law that relies on an intermediate that we've just suggested. It could be that the two NOs come together and make N2O2, and then N2O2 reacts with O2 to make two NO2s, right? I mean, that could be just as reasonable an answer. And so I can't base my rate law on an intermediate that I'm just surmising based on some knowledge of chemistry that we may or may not have, or some similar reactions we find in the literature. So I need a way to replace it. And as you guys move on, you're going to find that there are lots of really clever models that you can use to understand reaction kinetics more deeply. So if you want to learn more about the environment and study atmospheric chemistry, or if you want to learn more about enzymes in biology, or if you want to learn more about the metal organic frameworks that got the Nobel Prize this week, there are lots of approximations we can make in kinetics world. But again, we're just gonna say we're in IB right now, and we just need a first approximation. And the first approximation is going to be asking ourselves, how fast is NO3 made? Well, NO3 is made at a rate that is going to be proportional to these two materials coming together. That is NO and O2 colliding. And so what I am allowed to do is I am allowed to replace the intermediate NO3 with the product of NO and O2. That is, I know that the NO3 is made by that reaction. And so I can rewrite my rate law as K times NO times O2 times the NO we started with, or I can make that simpler. And so our rate law does in fact match experiment. So I was asked, are slow steps ever equilibriums? For us, no. For us, the slow step is, I'm not going to say that. I'm going to say, don't worry about it. I'm going to say, you just don't need to worry about it. So it could be that the slow step is an equilibrium, but it's going to lie very much to one side or another side. Like it just doesn't matter. It's not going to affect how we approach this calculation. We were just given a mechanism in which the first step was a rapid pre-equilibrium and the second step was slow. This is normally what we see for something like enzymes or for this reaction, like it's a common pattern, but I don't think you need to worry about that piece. So I tried to find a fun multiple choice question that would put these two ideas together. It's going to ask you to figure out experimentally what the rate law is, and then based on that rate law, figure out which of these possible mechanisms is most likely. So they're holding y constant. They're doubling x, and the rate is doubling. I'm going to open this up to any questions that you guys have in a minute. If you have any questions, I'm happy to answer them. I think this is just about the last question I prepared. So when the concentration of X doubles, the rate doubles. And so it's going to be first order in X. When X is held constant and the concentration of Y doubles, the the rate does not change. So it's going to be 0th order in Y. So using the method of initial rates to deduce the rate law was fine. Now we need to go on and we need to look at these different proposed mechanisms and try to figure out which one is the most reasonable. So for mechanism A, the rate law would be the rate of the slow step. And for elementary steps like these, so you can see the word step is there. You always know when it's a mechanistic step. We just take the reactants and raise them to their coefficient. So this can't be the right answer because it shows it being second order. For choice B, it's the second step that's slow. And so we would write down that the rate is equal to the rate constant times the concentration of the reactants. But this time the reactant's an intermediate, and that's forbidden. So we need to come up with a way of replacing that intermediate. So we can look before, and we can see that the intermediate I is made at a rate that is proportional to the concentrations of X and Y. So we would actually replace I with the concentration of X and the concentration of Y. For choice C, the first reaction is slow, so we could write down the rate law. That is the right answer. Yay. And for choice D, just to be a completionist, we would say that the rate is equal to, there's not enough room, trying to be a completionist and I'm failing. For choice D, we would say that the rate is equal to the rate constant times I times Y. And one more time, we'd have to get rid of that intermediate. How do we form I? Well, we form I in the first step. I is formed at a rate that is proportional to X. And so we would replace I with X. When I first started teaching IB, I tried really hard to make that description better. And I don't see a reason to overcomplicate it anymore. When you have an intermediate, you're going to go to the reaction where the intermediate was formed, and you're going to replace the intermediate with the reactants of the reaction where it was formed. So when you see this I, we replaced it with X. That's because I was formed from X. When we saw this I, we replaced it with X and Y. That's because I was formed by X and Y. So I don't try to do anything clever anymore. We could use an equilibrium constant to make this seem less like it's hand waving. But if you're taking exams in less than a month or just about a month, we now just are proficient at doing the calculation. We know how to replace an intermediate when writing a rate law. So there's like one more idea I had to share with you, and then I'm going to open it to you, and that is the Arrhenius equation written in its linear form is how we often calculate the activation energy of a chemical reaction. We measure the rate at a whole bunch of different temperatures and then use the slope of that line to determine the activation energy. So there are two ways this question can come up. In multiple choice, it's not going to be super numerical. It's going to give you some details. This detail says that reaction 1 has a larger frequency factor and a smaller activation energy. So if something has a larger frequency factor, it's going to have a larger y-intercept because this equation is carefully written in the form of a straight line. And again, it's in your data booklet. It's not something you have to memorize. You just have to see the linear connection. If I plot the ln of k on my y-axis, if I plot 1 over t on my x-axis, then the y-intercept is going to be the natural log of the frequency factor or the Arrhenius factor. And we know it has to be higher for reaction 1. So it's going to have to be this choice or this choice. The second thing we know is that the activation energy is going to be smaller. You can see that the activation energy is the slope. And so if the slope is smaller, it's going to be a flatter line. And so C is my best choice. Finally, if we don't want this to be qualitative, just trying to see that that's the expression for a line, and we want it to be quantitative, it is very common to get a question that says, here is the data, here is the natural log of k plotted versus 1 over t. Use this graph to figure out what the activation energy is. And you really find yourself picking 2 points on this graph and saying that the slope is going to be the rise over the run. And so I'm going to say it's like 13.24 minus 14.26 over 0.00343 minus 0.00319. And I'm going to put that in my calculator because I cannot possibly do that in my head. And I get minus 4250 is the slope of the line. And I really don't like that part, but I did it. And I know that the slope is equal to minus the activation energy divided by R. And the slope didn't have any units on the top. On the bottom, I had inverse Kelvin. And so the slope has units of Kelvin. So if I rearrange this formula, I would find that the activation energy is minus the slope times R. So it's going to be equal to 4250 Kelvin times 8.31 joules per mole Kelvin. And I've got to plug that in my calculator. And I get 35317.5 joules per mole. Of course, the question asked me to do it in kilojoules, so I get 35.3 kilojoules per mole. And I feel good about myself. It's a positive number. If you get a negative number, just change the sign. Activation energies have to be positive. So if you made like a little clerical mistake, as I'm very prone to, just make sure that you fix it when you box your answer. Okay, that's what I have. I believe that those are the main statements. The black ones are SL, the red ones are HL. We have gone through all of them, some of them super fast, some of them a little bit more carefully. I am happy to spend a few minutes answering any questions that you may have, or just to say thank you very much for coming and best of luck with your exams. Just trying to add a white page of paper. I don't seem to see the button right now. You're welcome. Thank you so much for coming. I can at least do something like that. Okay, I don't understand the Arrhenius equation or how to use it. So the Arrhenius, oh my goodness, that's very bright. The Arrhenius equation just explains how the rate of a reaction is related to a few of the parameters. I hope I can write on this. God bless America. I was hoping that I could switch apps to the one I am more accustomed to so I didn't look quite so awkward. It just wasn't working great this morning. There we go. Not quite. Okay, there we go. So the Arrhenius equation says that the rate constant is equal to some things. Is this the part you feel you don't understand, or is it the linear part? Okay. So collision theory said that for a reaction to be successful, we need to collide with the right orientation. And we need to have enough energy to overcome the activation barrier. And so Arrhenius said, hey, you know what? I can make this a math problem instead. I can try to explain what's going on. The rate constant says, let's look at the orientation or geometry factor. We call this the frequency factor. And it says, if two molecules were to collide, what are the chances that they would collide with the right orientation to react? So if I have H2 and I2, and they collide like that, that's not the right way. If I have H2 and I2, I'll be consistent, and they collide like this, that's going to work. Well, those are two really simple molecules, so the chances of them colliding right is probably pretty big. But if I have like some weird enzyme and I have some little tiny substrate, and the substrate's got to make its way into the active site, like the chances of my little substrate getting exactly where it needs to go in that enzyme probably, pretty small. And so that frequency factor might be a lot smaller for something as complicated as enzymes and substrates and all of that stuff. So that's what A is. It just tells you how likely is it that these two molecules are going to come together and have the right orientation. And there are some things I can do to make that better. I could stir my reaction, I could grind my stuff, I could do the reaction in the gas phase instead of in the liquid phase. I don't know if you have any familiarity with asthma, but like if you're having an asthma attack, you don't take the pill, you take the inhaler. Why? Well, the medicine is going to be nebulized into your lungs. And so it's going to do what it needs to do like instantaneously. It's going to be colliding with all the things it needs to collide with the right orientation. If it goes through your stomach, like sure, it'll get into your blood and it'll get there eventually, but the orientation, it's going to be slow as molasses. So we wouldn't do that if you're having an asthma attack. Okay, it includes the activation energy. If the activation energy is a really big number, then e to the negative, so that's 1 over e to the EA over RT, right? That would be another way of writing the second part of that. If EA is a really big number, when I raise e to that power, I'm going to get a really big number, but it's in the denominator. So the rate constant will be really, really slow. If the activation energy is high, then no one's going to do it. Uh, so that's what that means. And then temperature like mitigates that. So if I have something that's hard to do, what I could do is I could raise the temperature of the system so that more molecules are able to do it. So if I sat you down when you were in like when you were 6 years old and gave you your IB chemistry test, like you couldn't begin it. But we've been pumping you full of great information for the last 13 years, trying to teach you lots of stuff about science and math. Now you have the temperature, you have the ability to overcome this test. And so that's what that means. That's what the Arrhenius equation is trying to mean. The only way that I see us using it in class is in its linear form, which is also in the data booklet. You don't need to be able to write this down without having the notes. But I've just taken the natural log of the last equation. It's the same thing. It's just written in a different form. But when we write it in a different form, you can see that it has the expression of a line. So y is equal to mx plus b is my expression for a line. And so if I were to plot the ln of k on my y-axis and 1 over the temperature in Kelvin on my x-axis, then I would get a line that had a negative slope. And the slope of that line would be the activation energy divided by R. And the y-intercept of that line would be the natural log of the frequency factor. So a number of IAs that I've had students try to do is determining the activation energy of a process by actually measuring points along this line. So they'll do the same reaction at 5 different temperatures and then do some averaging, come up with this line of best fit, and solve for the activation energy. How to plot a graph with given values. Don't understand the question. Your test is only 2.5 hours for the paper 2 at HL, like no test is longer than that. I don't think you're going to be doing a whole lot of point plotting. Sometimes they'll have you add a point to a curve, but generally speaking, the curve is made. You might have to draw your best line of best fit through it. Yeah, so the values are typically given as ln of k versus 1 over t. So you just put them in as x and y. All right, I hope you feel a little better about the Arrhenius thing. You asked about nucleophiles a few times. That's what R 3.4 is about. It's about all the organic chemistry reactions. So you might want to spend a little time like reviewing. A nucleophile is something that loves nuclei, so has a negative charge and is looking for something positive to react with. So it's just a fancy word that means loves positive charges. My friend Aaron gave a review session on organic chemistry on Wednesday. So if you want to watch that, you certainly could. What is the equation for delta S? Delta H is reactants minus products, etc. So I think you're like confusing a few things. So I drew you this picture that had energy on this axis and the reaction coordinate, and it had reactants and products. And I said that I could tell you that the delta H for this reaction, which was the enthalpy of the products minus the enthalpy of the reactants, was going to be negative. or that this was exothermic. But your question makes it look like you're thinking about the various things like the delta H of a reaction is equal to the bonds broken minus the bonds formed. Is that what you're thinking about? Or it's equal to the sum of the delta H's of formation of the products minus the reactants. If that's what you're talking about, then S, entropy, like it's actually easier because there's only one way we do it. So, oh my goodness, I don't remember my section numbers right this minute, but whatever section the enthalpies of formation are in the data booklet, that's where we get delta S also. And delta S uses the same formula. So I believe that this equation is in the data booklet now. The delta H of combustion is also in the data booklet now, but it is the reactants minus the products. So these two equations are in the data booklet. You don't need to memorize them. You do just need to make sure that when you're using the tables, that you use the right one. All right, I appreciate you coming. I hope you have a wonderful rest of your day. Thank you very much. Bye.